friend Sky might have proven the Riemann hypothesis. In the year 2000, the Clay Mathematics Institute set up seven $1 million prize bounties for the solution to the biggest unsolved math problems in mathematics. Only one prize out of the seven has been claimed so far. And of the remaining six, I think it's fair to say that the best well known and the most notorious problem is known as the Riemann hypothesis. My goal in this short series of videos is to show my friend's proof in a way that a bright high school graduate with an interest in math would be able to follow. Now, making it that clear and easy is a pretty big challenge in itself. It's a work of translation, but I think it'll be fun to try. So here we go. In this first video, I want to introduce what it is that my friend Sky is trying to prove. So first, what is the Riemann hypothesis anyway? To sum up, back in 1859, Bernard Riemann published a paper containing the original formulation, conjecturing that his Riemann zeta function, which takes a complex number s as its input, has its zeros only in certain places. So here's the t-shirt version. Yeah. It turns out that this conjecture has important implications about the distribution of prime numbers, among other things. And even though it seems true, like as far as we've been able to check it, mathematicians so far haven't been able to prove it completely. Maybe until now. However, I'm not actually going to teach the Riemann hypothesis in detail in this series, at least not in its original form. For that, I recommend you check out another channel called Zeta Math, which does a great job, like deep diving into the Riemann hypothesis in that way. But fair warning, expect multiple hours of in-depth mathematics over there. What I'm going to show you is a different statement called the Landau hypothesis that turns out to be exactly equivalent to the Riemann hypothesis. And this is just one of many forms that the Riemann hypothesis takes. One of the ways we can see how deeply important the Riemann hypothesis is that there's all these different versions of it that look different, but each of them turns out to mean exactly the same thing. And for any given reformulation of the Riemann hypothesis, it is strictly true that the Riemann hypothesis is true if and only if the reformulation is true. They're interchangeable. And lucky for us, the Landau hypothesis, which is the particular version of the Riemann hypothesis that is being approached by my friend's paper, is actually a lot easier to explain and understand than the original. So let's take a look at that. We're going to begin with the fundamental theorem of arithmetic. That states that each integer has a unique prime factorization, and that means there's one and only one way to express it as the product of primes. So for instance, 9 equals 3 times 3, 10 equals 2 times 5, 11 is prime, so it just equals 11, and then 12 is 2 times 2 times 3, and so on. You can do this for any number. And there's only one way to do it for any number. That's what we're saying here, right? Order doesn't matter, right? We're considering that 2 times 5 is the same as 5 times 2. But you can never have some totally different set of prime numbers that just accidentally comes out to the same product. Like you couldn't accidentally discover something like 7 times 7 equals 2 times 5 times 5. The left side is 49, the right side is 50. So they're close, but they're not equal. Each number has a single, unique prime factorization. And when we're studying prime numbers, that unique prime factorization is sort of like the secret identity of that number. That's the way I think about it. Like in some important way, the identity of 49 is that it is 7 times 7. That's what it is. Let's do that a different way. we're going to write each number as a product of first all the prime numbers, uh, but with exponents. So first we're going to write down, 9 equals 2 times 3 times 5 times 7 times 11 times 13, and just keep going, all the prime numbers, right? So you set it up like that for each number, and then you make it true by adding the exponents, like this. And we can do this because we have available to us the exponent of 0. And if we raise any number to the 0th power, we get 1. And if we multiply by 1, it doesn't do anything. So more or less, we can build a number by starting all the exponents at 0 and then increment the ones that we actually need, like this, right? So 9 is actually just 3 times 3, and it doesn't matter how many times we multiply it by 1. 10 is 2 times 5. This image is going to become important later on, so let's take a moment to appreciate what we're doing here. There's an infinite number of primes, and pretty much all of them are going to have an exponent of 0, but there will be some exceptions on each line to build up the number that we're after out of its unique prime factors. The exponents themselves could be thought of as another way to express the identity of that number. We could have a secret code where 9 corresponds to a series 0, 2, 0, 0, 0, 0, 0, 0, or 10 corresponds to a series of 1, 0, 1, 0, 0, 0, and so on. If I gave you one of these codes, you could take it and rebuild the number it came from, right? You raise the prime numbers to those powers and multiply it together, and you get back the number that I used to generate the sequence. Now, here's something I want you to think about for a moment. Not only does each number have a unique prime factorization and therefore a unique series of exponents that are associated with it, but every possible series of exponents that you could just, invent can be used to create a unique number. Like I could just list some numbers like 1, 2, 0, 0, 1, 0, 0, and that represents a number, even if I haven't calculated which number I'm talking about. In this case, let's see, 2 times 3 times 3. There's no 5s, no 7s, and there's going to be an 11. So we get this. 2 to the 1 times 3 to the 2 times 11 to the 1, we get 198. And the only catch is, of course, the series has to finally end in all zeros, right? You can't just have like a repeating 1, 1, 1, 1, 1, 1, 1 forever, because that would mean that we're multiplying together all the prime numbers, 2 times 3 times 5 times 7 times 11 times 13, just without stopping, right? And that blows up. So when we talk about these, what I'm calling code forms of the numbers, they have to be finite, right? The non-zero part of them has to be finite. And then we just, slap on repeating zeros at the end. In other words, there must be some last non-zero exponent after which all the exponents are 0. And as long as that is true, the exponent series defines a unique positive integer n somewhere on the number line. And that series represents the only way to express n as a product of prime numbers. Cool, right? The Landau hypothesis. So we're almost done setting up the Landau hypothesis. But I will say hold on to your hat because this gets weird fast. Let's say we sum up the exponents that are associated with each number n. And we know that that sum is finite, right? So we can add them all together and find out what they add up to. And we're going to call that omega of n. Because we're doing serious math now, so we got to start using Greek letters. Omega of 9 is 2. Omega of 10 is 2, right? That's 2 times 5. Omega of 11 is 1. That's going to be true for all the prime numbers. And omega of 12 happens to be 3, and so on. And we can do this for any number. So that's omega. Now we're going to define the Liouville function, lambda of n, is equal to -1 raised to the power of omega of n. So what does that look like? Well, lambda of 9 is -1 squared, which is +1, right? And same for 10, we get a +1. Lambda of 11 is going to come out to -1 because we raised -1 to the first power, so it's just itself. And then lambda of 12, -1 to the third power, is -1. Oh, I see now. Basically, if omega is even, you get a +1, and if omega is odd, you get a -1, right? So this is some kind of yes-no signal telling us if the number of primes in the prime factorization of n is even or odd. Okay. But there's more. So let's make a table. Here we're going to start at 1 now, and we're going to write the values for omega of n, and hopefully you agree that I've done that correctly. And then we put in lambda, right? We raise -1 to that power. We get either a plus or -1 on every line. Okay. Now, we're going to take all these integers in order, starting from 1, and add up the Liouville function results, the lambdas. And we're going to call this the summatory Liouville function. So let's put that in the fourth column. The first one is just the 1 that we get for lambda of 1. And then when we get down to line 2, we add the -1 to that 1, and we get a 0. And then for n equals 3, we get another -1, so we add that to the 0, and we get -1. And then we add +1, and we get a 0, and -1, we get -1, and so on. And we have a running total. So now we're going to ask the question, how does that running total behave? And the Landau hypothesis states that as you go along, this total becomes small relative to the square root of n. Or in technical terms, the limit as n goes to infinity of the sum of lambda up to that value of n when divided by n raised to the power of 1/2 plus epsilon is equal to 0 for any positive epsilon. Clear as mud, right? Okay, I'll talk about this a little more for those who are new to thinking about limits. Epsilon is some arbitrary positive number. As epsilon gets bigger, the denominator gets bigger, and of course it's easier for the expression to go to 0. But the smaller epsilon gets, the harder it is for this to be equal to 0. And we're stating that this is true for all positive values of epsilon. So in order to prove that this statement is true, we have to investigate the cases where epsilon gets very, very, very small, very close to 0. Since epsilon can get arbitrarily small, n raised to the 1/2 plus epsilon should be thought of as a number that's like very close to n to the 1/2, or the square root of n, okay? Now, as n grows, the square root of n also grows, right? Heading for infinity in its own slow way. And the summatory Liouville function also might grow, and it will. But the Landau hypothesis is suggesting that it does not outpace the square root of n, okay? If it grows as n increases, it at least does so at a rate that's equal or slower to the square root of n. So that is the thing that we are interested in proving. We should talk about this a little more, though, just to get clear on how tricky this topic is. Here's a picture of the summatory Liouville function, summing up those positive and negative ones, all the way up to n equals 10,000. Found this on Wikipedia. Now, let's get a handle on this image. Note that it's negative. That is, at least in the beginning, there's a lot of numbers with odd numbers of prime divisors. For example, all the primes themselves have 1 divisor, so that gets you a negative 1. But it has been proven already by somebody else that as the path continues, there are infinite examples of both positive and negative values, meaning it does eventually meander back over the 0 line into positive territory, not just once, but an infinite number of times. So there are infinite examples of a number n where, if you consider the integers from 1 to n, there's a perfect balance between those with an odd number of prime factors and those with an even number of prime factors. That's hopeful, right? But it doesn't prove what we want to prove. Even knowing that, it would still be quite easy for the Landau hypothesis to fail. For example, here is a different series of +1s and -1s that I cooked up just as a simple counterexample. So the definition, very simple. It takes a value of +1 until the sum reaches n to the 0.55 power, a little bit over n to the 1/2. And then it switches to -1 and goes back down until the sum dips below 0, and so on. And under this very simple rule set, it gets out past the square root of n like 6 times before n even reaches 100. And in between, it dips below 0, every time. And it'll continue that behavior forever, stubbornly failing to go to 0 for values of epsilon less than I guess 0.05, right? And as we think this over, we realize that staying inside of root n is actually kind of remarkable for a sum of 1s and -1s that come from some non-random process. What if it was random, though? Okay, this is a kind of a tangent, but I think it helps. If you were to stipulate that the plus and -1s that you're summing are coming from random coin flips, you can conclude that probabilistically the series does converge for root n. So the Landau hypothesis is sort of like saying that the +1s and -1s are distributed somewhat similarly to random chance. Okay, there's a neat paper on this. I'm not going to go more into it because I don't want to get too far off track. But I did want to mention it. It's kind of cool. In case you're interested, you can go check it out yourself. And I also wanted to mention that one of the authors of that paper is the late great Tom Osler. Yes, winner of the 1965 Philadelphia Marathon, and a dedicated teacher of mathematics who taught both myself and Sky back in our undergraduate days when we were becoming friends. And Sky's paper is dedicated to Tom. Truly a great guy. Final thing I want to point out. This is just a warning to the casual viewer about how hard this stuff is. Is that the order of the positive and -1s actually does matter. You could take a series of plus and -1s that does converge over root n. You can reorder those plus and -1s and find out that the new series does not converge the way that the old one does. And that doesn't mean you've lost or misplaced any of the items that you're counting. They just sum differently because they're being tallied up in a different order. And that would be insane if we were talking about a finite collection of things. But that kind of issue is actually very typical of mathematics anytime you get involved with infinity. This stuff is just hard. It's fundamentally hard. Anyway, now we know what we're trying to prove, right? And in the next video, I am going to go right into Sky's paper. We're going to talk about how he begins to set up his proof of the Landau hypothesis. And if you remember this, we're going to harken back to this in a neat way before long. So see you next time. Thanks for listening.